Okay, so this is our actual title, and it's really long, so we made like a false title page because it's way faster. So we wanted to, the title of our thing is the determination of oxyhemoglobin concentration through the Beer-Lambert law and spectrophotometry, which is our super long actual title. So
the purpose of this lab was to determine the oxyhemoglobin concentration in a sample of blood using spectrophotometry and the Beer-Lambert law, which we will explain later. And then another one of our purpose of the lab was to perform the experiment in a cheap and efficient way, so making our own materials and having like a limited budget, pretty much. And then our hypothesis was that the concentration would be within 10% of the actual concentration, and this was kind of just an arbitrary approximation. And then the experiment would also be feasible to perform with our limited budget.
Alright, so like first, if anybody doesn't know what hemoglobin is, it's like the stuff that can carry oxygen, or basically, for the most part, it carries oxygen through your blood, into your lungs, and your brain, lets you like function. So some background, basically there's one principle that this experiment uses, and it's the Beer-Lambert law, which says that absorbance is equal to the molar absorptivity coefficient times the length of what the light is passing through times the concentration. So that explained kind of through diagrams is like, it's really intuitive. When you pass light through like a substance in some kind of holding device, the initial intensity of that light and then the final intensity of that light is going to be like somewhat proportional to the absorptivity of the substance, which is, you see there's like a substance that is more concentrated will absorb more light. Also a substance that has more space to pass through, or light that has to pass through a space wider, will have higher absorptivity as well. So it's kind of described here what absorbance is. Also, some additional background is all substances or compounds, molecules, atoms absorb light differently. They have different spectra, so they'll absorb different wavelengths of light in different ways. So here we have a spectra plotted for the absorption of hemoglobin and of oxyhemoglobin. You can see that there are peaks that are local to specifically the oxyhemoglobin around here and here, which we'll talk about later, as well as a peak here which is not specific to the oxyhemoglobin, which we'll also talk about later. Yes.
The distinction between those two things is just whether it's carrying oxygen right now or not?
Yes.
Yep.
Okay.
So basically to perform this experiment, we use spectrophotometry, and we use a spectrophotometer. And this is basically how it works. There's a light, it passes through a lens, goes through a prism, and then using the spectrophotometer, we could pick the specific wavelength that we wanted to shine through the sample, and then that measured pretty much how much of that was absorbed.
So the procedure was really long. Basically, it involved a lot of sketchy home organic chemistry. I had to make because we wanted to make everything ourselves and see how feasible it was to do this. We didn't just buy anything. So basically, you can read through this. I had to make this buffer. This is to isolate the hemoglobin, which took a ridiculous amount of time. You had to allow the hemoglobin to combine with air because that gave us the oxyhemoglobin complexes. And then this pretty much from 5 down describes our procedure for the performing of the experiment to find the concentrations and the absorbance spectra of the oxyhemoglobin.
And we had to use a centrifuge which spun the blood around really quickly, so it separated into the plasma, and then the red blood cells would be at the bottom. And the centrifuge we found in the chemistry storage room was ancient, and we had no idea how fast it was actually spinning, so that was kind of interesting.
Yeah. So also, just so you guys know, we used cow blood, not people blood.
So you did buy something.
So we had to buy cow blood, and then all the rest of the chemicals came from an old chemistry kit that I had in my basement. And I have a bunch of chemistry supplies in my house because my mom used to be a pharmacist. So she has a bunch of stuff from school. Shout out to her because she helped with a lot of the calculations for molarity and stuff because I'm not good at that. Yeah. So this is our procedures, kind of pictures. We don't have one. This is also kind of a diagram because we had a lot of different setups. So just showing you a single setup would be kind of pointless because it ranged anywhere from a vial in the spectrophotometer to a pan on our stove trying to distill out some kind of salt. So,
And we were safe, we used gloves.
yeah, we used gloves and goggles, just so you guys know. So this is really hard to see, but I was super excited because this is actually when we successfully isolated the red blood cells from the blood itself. So I mean, this is just water on top, but those are the physical red blood cells. All right. So this is the absorbance spectrum of oxyhemoglobin that we got. We have wavelength on the bottom and absorbance on the y-axis. So you can see that we have peaks here, here, and here, which we'll talk about in a minute. So,
So pretty much those peaks were at these 3 wavelengths, and we took known concentrations of blood, and we found the concentrations at those specific wavelengths. You could adjust it using the spectrophotometer, and using the Theyre-Lambert law, we were able to calculate the coefficient, epsilon, or the absorptivity coefficient.
So the way we calculated the absorptivity coefficient is by rearranging the Theyre-Lambert law so that the slope was equal to the absorptivity coefficient. So you plot absorbance, which is a unitless, absorbance is unitless, I guess, versus the concentration times the concentration of the substance, which was known, times the length that substance had to, the light had to pass through that substance. What we get is this is at 419 nanometer wavelength of light. This is at 537 nanometers wavelength, and this is at 571. So those are all 3 of the peaks that we noticed. Yes.
In these graphs, are you varying length or concentration?
We are varying concentration.
And
sorry, the length was constant.
The length is also happens to just be 1 because that's the distance of the cuvette. And interestingly, the length is in centimeters, not meters.
So, yeah, so actually what we get is an interesting trend with these, which we will talk about in our conclusion too. So,
and this pretty
curve,
much explains the standard curve. So with a standard curve, if you have some known absorbance, you can essentially draw like a dotted line over, and if you have this line, the concentration value should fall on this line, so it should be the x coordinate.
Yeah, so basically you extrapolate unknown value to find an unknown value along that line.
And then for our final experiment, we took some blood with unknown concentration, and we essentially found its absorbance using the spectrophotometer, using those wavelengths that we had already determined, and we used the coefficients that we determined for those specific wavelengths.
So here's our final calculations on HbO2 concentrations. HbO2 is oxyhemoglobin. We get concentrations that are in molarity, which is really small, but it's actually not super small because hemoglobin is these huge particles, so it actually accounts for like a fair amount of the red blood cell's mass. You have some error here. What we find is that our error is actually like pretty reasonable for the amount of places where it could have gone wrong in this experiment, except for at 419.2, when we used the 419.2 nanometer wavelength passing through. And the reason we think that is because if you look back at that original spectra we had taken off of the internet of the known absorbance values of oxyhemoglobin and hemoglobin, what you find is that a peak around 419.2 is not local to the oxyhemoglobin itself, so we may have not been measuring anything at all, or we may have been measuring hemoglobin, or we don't really know, but we know that that peak is not specific to oxyhemoglobin.
So why is this important? Essentially, a pulse oximeter, which is like a medical tool, functions on the same principle. It shines like a little infrared light through like the capillaries in the tip of your finger, and it's able to use find the intensity passed of the light on the other side, and from there calculate the oxygen levels in your blood.
All right, conclusions, both hypotheses were rejected. The first, that it would be within 10%, that was not correct. We were actually fairly close with these calculations, or with our error, but it still wasn't within 10%, so it wasn't really cheap. It didn't cost us $700, but if you were to do this from scratch, it would, because the centrifuge is really expensive. If you didn't have to buy all the chemicals that I just happened to have laying around my house in that chemistry set, it would be really expensive. The blood was $16 for a bag, and we had to get 2 bags because we messed up. It took a really long time, so that's why we didn't get to plot extra data, because physically getting the hemoglobin itself took me like a week, which was awful. Why did they look funky is actually the relationship for a standard, the linear relationship for a standard curve falls apart at extremely low and extremely high concentrations. So we think that we may have reached the bounds with those absorbance when we used the wavelength of 537.1 and 575.1 nanometers passing through. We may have reached the bounds of what is actually a linear relationship on the low end, because that was a really small concentration we were using. So that's why it may have kind of flattened out. We kind of talked about the peak at 419 at 0.2 nanometers is not really local to oxyhemoglobin itself. And the pulse oximeter, Max already said, so that's it.
Because of the incredible depth of this experiment, I'm sure there are a million questions. We'll have to hold them, except I am the teacher, so I get to ask one. Can you go back a long way to the spectrum that you found on the SpectroViz? Yes. You're looking at hemoglobin, right?
Oxyhemoglobin.
Okay, but that's a red thing, right?
Correct.
Why does it say that the absorbance is so low in the red?
Isn't it that things appear, I mean, I don't want to say, I'm not really sure. Donovan? It's that like things appear the color that they reflect the most or something like that, I'm pretty sure.
So do you mean that it is not absorbing the red?
Yes.
But rather that it is... Very good. Thanks again.
All right. A substance that is more concentrated will absorb more light. Also, a substance that has more space to pass through, or light that has to pass through a space wider, will have higher absorptivity as well. So, I mean, it's kind of described here what absorbance is. Also, some additional background is all substances or compounds, molecules, atoms absorb light differently times the length of what the light is passing through times the concentration. So that explained kind of through diagrams is like, it's really intuitive. When you pass light through like a substance in some kind of holding device, the initial intensity of that light and then the final intensity of that light is going to be like somewhat proportional to the absorptivity of the substance, which is, I mean, you see there's like
Limited budget.
Alright, so like first, if anybody doesn't know what hemoglobin is, it's like the stuff that can carry oxygen, or basically, for the most part, it carries oxygen through your blood into your lungs and your brain, lets you like function. So, some background. Basically, there's one principle that this experiment uses, and it's the Theyre-Lambert law, which says that absorbance is equal to the molar absorptivity coefficient.
One of our purpose of the lab was to perform the experiment in a cheap and efficient way, so making our own materials and having like a limited budget, pretty much. And then our hypothesis was that the concentration would be within 10% of the actual concentration, and this was kind of just an arbitrary approximation. And then the experiment would also be feasible to perform with our...
Okay, so this is our actual title, and it's really long, so we made like a false title page because it's way faster. So we wanted to, the title of our thing is the determination of oxyhemoglobin concentration through the Theyre-Lambert law in spectrophotometry, which is our super long actual title. So
The purpose of this lab was to determine the oxyhemoglobin concentration in a sample of blood using spectrophotometry and the Beer-Lambert law, which we will explain later. And then another